Today we are going to discuss multilinear maps and tensors. This is a prerequisite to our next lecture, which we are going to discuss tensors and differential forms on manifolds. So in today's lecture, we are mainly in the level of algebra and linear algebra. We discuss multilinear maps and linear tensors and linear forms. In the next lecture, we are going to carry them to manifolds. So differential forms and tensors are essential in the study of manifolds. Many geometric objects like Riemannian metric, curvature, they are defined as tensors. Many interesting structures on manifolds are defined using tensors and differential forms like symplectic structure, complex structure, Calabi-Yau structure, etc. So these two lectures are going to be kind of basic and foundational for the things we are going to discuss later. Okay, let's start with the definition of multilinear maps. So the first thing we are going to define is what is a multilinear map. So let's say we have a few vector spaces. So here today everything is over R. So we have a few finite dimensional vector spaces V1, V2 up to Vk, right? So let's denote these vector spaces by V1 up to Vk. Okay, great. Now I would say a map T from the product of these spaces, V1 times V2 up to Vk to R is a multilinear map, if it's linear in each component, in each coordinate. If we fix for each I, if we fix, say for any I from 1 to k, if we fix the other k minus 1 coordinate and only look at the ith coordinate, it would be linear in that coordinate. So let's say if V1 is a vector in the vector space Vi minus 1 is a vector in vector space Vi minus 1. Vi and Vi prime are two vectors in the vector space Vi, and then up to Vk in the vector space Vk. So we use small letters for vectors and capital letters for vector spaces. Also, let's say C is a constant real number. So I would say T is multilinear if T of V1 up to Vi minus 1 and then Vi plus CVI prime and then up to Vk would be equal to, so it should be linear in the ith coordinate for each I. So it should be equal to V1 up to Vi and then the rest up to Vk plus C T of V1 up to Vi prime, and then the rest, we would then touch the rest up to Vk. So if we have this for every I from 1 to k, we say T is multilinear. Okay, so this is the first definition of today's lecture. Okay, now let's define tensor product of linear maps. So let's say we have a vector space, again, vector spaces V1 up to Vk and linear maps Fi from each Vi to R. So we have F1, F2 up to Fk. Each Fi is a linear map from Vi to R. Now we can define tensor product of F1, F2, F2 up to Fk. So we denote that by F1 tensor, F2 tensor up to tensor Fk. So we are going to define this product in a way that it would define a multilinear map from V1 times V2 times up to Vk to R. How are we going to define this? So in order for me to tell you what is the tensor product of F1 up to Fk, I should say what is the value of this map on any k tuple of vectors, V1, V2 up to Vk, where V1 comes from the vector space V1 up to Vk comes from vector space Vk. I should tell you what is the value of this kind of F1 up to Fk on V1 up to Vk. And note that F1 of V1 makes perfect sense, right? F1 is defined on the vector space V1. F2 of V2 is defined up to Fk of Vk. Now, the point is that each Fi of Vi is a real number, right? F1 of V1 is a real number. F2 of V2 is a real number. Same goes up to Fk of Vk. So we simply consider the product of these real numbers. We get another real number. So that completely defines what is F1 tensor up to Fk. And it's a good exercise to check that this is indeed a multilinear map when each Fi is linear. Okay, so we had tensor product of linear maps at this point. So it's important to have that in mind, right? Okay, so let's get back to our vector spaces. We want to vk. To each vector space, we can assign another vector space called the dual space. We denote them by v1 star up to vk star. So v1 star is the dual of v1, vk star is dual of vk. So just a reminder, the dual of a vector space vi is the set of linear maps from Vi to the base field, which here is taken to be the real numbers R. Okay, so a vector space and its dual space, they have the same dimension. Their dimension would be equal. Okay? So now consider this new space. Consider the space of multilinear maps from V1 times V2 times up to Vk to R. Consider this space. We denote this space. We have a notation at this point for this space. Note that this space itself is a vector space. It's a good kind of good practice, good exercise to check this. If you pick two multilinear maps, their sum, vector sum, is another multilinear map, etc. for scalar product. So we denote this space by v1 star tensor, v2 star up to tensor vk star. We call this the tensor product of these dual vector spaces. Note that previously we learned tensor product of linear maps. Here we are defining tensor product of dual vector spaces. So these tensor products are defined on different levels. So mentioning that this space is a vector space, it's natural to ask what is the dimension of this vector space, right? So from linear algebra, we know the correct way to kind of decide what the dimension is, or one way is to find the basis for that vector space, a basis for that vector space. Okay, that's what we want to do. So suppose V1 star up to Vk star, they're finite dimensional vector spaces. Each of them has a finite basis. So let's say V1 star is generated by the following basis. Let's denote F1, F2, up to F with superscript dimension of V1. There are V1 dimension, V1 many vectors generating V1 star. Let's add a subscript 1 just to say these are the basis of V1 star. Let's do the same for all of these vector spaces. So Vk star is generated by F1k, F2k, up to F dimension of Vk. So these are vectors in Vk star generating this space. So now we have basis for each of these vector spaces. From these, I can construct a basis for the tensor product space. Look at the first line. Pick any of these F1 i's you want. So let's denote that with F1, I1. Let's look at the second line, V2 star, which I have not written it. Pick one of the elements from there, etc. Up to the last line, Vk star, pick one of the vectors from V1k up to V dimension Vkk. So if we consider tensor product of these, it would be an element in the tensor product of V1 star up to Vk star. And in fact, if you consider all different choices you can make from each line, you get a basis for this space. So how many choices do we have for F1, I1? We have dimension of V1 many. How many choices we have for F2, I2? Dimension of V2 many. Up to the last one, how many choices do we have for FKIK, dimension of VK many? So the product of these dimensions is the dimension of the tensor product space. Okay, so that's the way to come up with a kind of a basis for the tensor product space. Okay, let's now define a new concept. Suppose we have T, a multilinear map, let's just say a multilinear map. on V1 up to Vk. So T is an element of V1 star up to Vk star. Let's say S is also a multilinear map on another set of vector spaces. So let's say S is an element in Vk plus 1 star up to Vk plus L star. We want to define the tensor product of these two multilinear maps in a way that it would be a multilinear map defined on V1 star up to Vk star to V tensor Vk plus 1 star up to Vk plus L star, right? That's what we want to do. We want to define tensor product in a way that this would hold. Okay. So in order to completely characterize what T tensor S is, as a linear map from V1 times up to Vk times Vk plus 1 times up to Vk plus L to R, I should say what is the value of T tensor S on every k plus L tuple of vectors coming from these vector spaces. So I should say what is T tensor S of V1, where V1 comes from the vector space V1, Vk comes from vector space Vk, etc., up to Vk plus L. We should define this value, right? Now notice T itself is a linear map, a multilinear map from V1 times up to Vk. So T of V1, V2 up to Vk is defined, right? That's what it means when we say T is in V1 star tensor up to Vk star. It means T of V1 up to Vk is a real number. Right. Same holds for S. S of Vk plus 1 up to Vk plus L is a real number, right? So these are two real numbers. So we simply consider the product of these two real numbers, which would be another real number. We define that as the definition of T tensor S. And it's a good exercise again to check if T and S are multilinear. With this definition, T tensor S is also multilinear. So T tensor S is a multilinear map. So previously we defined the tensor product of linear maps. This is kind of a generalization. Now we are extending that previous definition to tensor product of multilinear maps. This tensor product satisfies the kind of good properties you want. For instance, T1 plus T2 tensor S would be T1 tensor S plus T2 tensor S. Same thing holds if I consider S1 plus S2. This. Um, it's also associative. So if we have RST three multilinear maps, the order we consider the tensor product doesn't matter. You can first consider R tensor S and tensor that from right with T, or first we can consider S tensor T and tensor that from left by R. It's not commutative. It might not even make sense in general to consider commutativity. This is not correct. Okay. Let's just introduce a vocabulary. For any vector space Vi, any element in the dual space of that can be called a one tensor. That's just the name, right? It's just so one tensor is just a linear map from Vi to R. And if you pick any element in V1 star up to tensor up to Vk star, we call that a K tensor. So it's a multilinear map with domain being product of K vector spaces. We call that a K tensor. Okay, so tensors at this point are just multilinear maps for us. Okay, a remark. So think about V and W. Now consider V tensor W star. This space can be identified in a kind of canonical way with the space of linear maps from W to V. So consider the space of linear maps from W to V. We denote this space by L of WV. So that's just a notation. LWV denotes the space of linear maps from W to V. These two spaces can be identified. So let me give you a hint. Actually, this is more than a hint. This is essentially the answer, how to identify these two spaces. Pick an element from V tensor W star. So in general, it's not of the form V tensor T, but let's consider a simple case where we have V, a vector from V, and T, a vector from W star, which means it's a linear map from W to R. Consider their tensor, V tensor T. I want to say it uniquely identifies an element in LWV. It uniquely can be understood as a linear map from W to V. So it means, what does it mean it can be understood as a map from W to V? It means if you give me a vector in W, denoted by the small w, I can define a vector in V to be as the output of this function, right? Now look at T of W is a real number because T is a linear map defined on W. So I can simply multiply this real number, this scalar, by the vector V. It would be something in V. So V tensor T defines a linear map from W to V, right? That would be the thing I would associate to V tensor T on the right-hand side of this identification. It's good to think how this identification would extend to the whole spaces. Okay, just a few notations. So tensor KLV, by that notation, I mean V tensor V tensor V K times tensor V star tensor V star tensor V star L times. That's the notation we are using for the tensor product of the vector spaces and their duals. Another notation some people might use is that tensor KV tensor L V star. Any element inside this space, any T inside this space is usually called a KL tensor. So the first thing means the number of like elements coming from V. The second means the number of things coming from V star. So with this notation, tensor 1, 0, V is just V. Tensor 0, 1, V is just V star. And just as a convention, tensor 0, 0, V is just the base field, which the base field here is the set of real numbers, R. Okay? Great. So these are just some notations we are going to use pretty frequently, actually. Okay, now it's the time to discuss linear p-forms. These are the linear version of differential forms which we are going to see later. So what do I mean by a linear form? Suppose T is an element in the tensor product of V star K times. So T is a map from V times V times V K times to R. Right. Great. So what do I mean by the map to be P form, a differential form? So let's first define a kind of simple algebraic thing, which you might have seen in algebra or combinatorics, permutation. What do I mean by a permutation? So any one-to-one map from the set of natural numbers 1 to up to some k to itself, so it's injective and surjective, 1 to 1, is called a permutation. Let's look at one example. For instance, suppose k is 4. I have the set of numbers 1, 2, 3, 4. Now, think about a one-to-one map from these, which sends 1 to 3, 2 to 1, 3 to 2, and 4 to 4. Okay? If I denote the map with sigma, it would be sigma 1 is equal to 3, sigma of 2 equals 1, sigma of 3 equals to 2, sigma of 4 equals 4. Great. So this is a permutation. I assign a sign to each permutation, which is either +1 or -1. How do I define that? Look at the number of intersections between those arrows. If the number is even, I define the sign to be +1. If the number of intersections is odd, I define the sign to be -1, right? Also assume the intersections are always transverse. There wouldn't be like tangential, Great. So with this definition, we are ready to define the notion of linear forms. So I would say K tensor T is symmetric, if if you look at the value of T on any set of vectors V1 up to Vk, the order of V1 up to Vk doesn't matter. In other words, if you change the order of these vectors following a permutation, the value of T would stay the same for any permutation and any set of vectors V1 to Vk. So the space of permutations on K element is denoted by Sk. So it means for any permutation, T would stay the same. And T is called alternating if it kind of depends on the permutation, but not much. It depends on a permutation in a very specific way. So again, if you have set of vectors V1 up to Vk, if you change the order following a permutation, the value of T would change, but only by multiplication with the sign of the permutation. So it might be +1, it might be -1. So there's just a plus minus behind the K in the K tensor. Okay. Yeah, so this is kind of quite essential, especially alternating tensors play an important role. So now there is a way to make any tensor alternating. So we define a map denoted with alt, which sends any k-tensor to an alternating k-tensor. So we send any k-tensor to an alternating k-tensor. How does it work? Suppose we have T, a k-tensor, right? It might be alternating, it might not be alternating. We define alt of T by the following formula. So 1 over k factorial. You can ignore that for now, it's just a normalizing constant. So this is the main part. Consider any permutation on k numbers. So Sk is the set of all permutation on k numbers. Consider the sign of the permutation and multiply that by T composed with permutation. What do I mean by T composed with the permutation? This is just a notation. So T O sigma, if you plug in V1 to Vk, I define it to be T of V sigma 1 up to T V sigma k. So taking sum over all these, dividing by k factorial, that would be the definition of alt of T. So just with this new notation, T is symmetric if T equals T O sigma for every permutation sigma. And T is alternating if T O sigma equals sine of sigma times T for any sigma. Right, just a way to kind of make things a bit more concise. Okay, so now the claim is that no matter what the k-tensor T is, alt of T is an alternating k-tensor. So it's a good exercise to kind of verify this and make sure this is correct. So I denote the space of alternating k-tensors by lambda k v star. So it's a subset of k-tensors. This is the set of k-tensors such that T is alternating. So this is a subspace, in fact. And this subspace is a vector space. So this is a sub-vector space. Anything inside this space is called, any alternating k-tensor is called a k-form. So I say T is k-form if it's an alternating k-tensor. This is just a new word, right? If the TV start with this alternating, then alt of t equals to t. So that 1 over k factorial is actually for this. Max, if we wouldn't divide by 1 over k factorial, there would be a constant somewhere in this equation. Okay, great. Now, as the next step, we define the suitable product for K-forms. It's called wedge product. So the point is that if we pick two alternating K-tensors, let's say T is an element of wedge KV star, so it's a K-form. S is an element of wedge LV star, so it's an L form. their tensor product is not necessarily a K plus L form. It's not necessarily true that it would be another alternating tensor. This is not necessarily the case. We want to define a new product, which we denoted with T wedge S. We want to define it in a way that it would be an alternating tensor. So it would be an element of uh, the alternating K plus L forms on V. Okay, how should we define that? So we define T wedge L to be the alternating map applied to T tensor S. Again, there is a kind of a constant K plus L factorial divided by K factorial L factorial. That's just, again, a normalization thing. So this would be an element of lambda K plus L V star. So wedge defines something from lambda K V star times lambda L V star to lambda K plus L V star. So this wedge is like a map which takes two inputs, T and S, and the output is T wedge S. So it gives you another alternating tensor or K plus L form. So this wedge product also satisfies the good conditions you want. It also has this property that T1 plus CT2 wedge S is T1 wedge S plus CT2 wedge S. It's also associative, just like the tensor product, doesn't depend on the order. So the next question is that, is it commutative? So is T wedge S the same as S wedge T? Not necessarily. It's equal to minus 1 to the KL, where T is a K form and S was L form. So it's up to plus minus. Now suppose we have F1 up to Fk. Suppose these are linear maps from V to R, so there are elements of V star. We can consider their wedge product, V1 wedge V2, sorry, F1 wedge F2 up to wedge Fk. This would form a multilinear map from V times itself K times to R. So this wedge product, F1 wedge F2 up to Fk, as an input would take K vectors in V. So the input would be V1 up to Vk. So what is the value of this thing? It's a good exercise to compute this explicitly. So to kind of get an intuition, let's consider the case where K is equal to 2, F1 wedge F2 acting on V1, V2. So we should consider all permutations on two numbers. This set is denoted by S2. There are two maps from 1 to 2 to 1 to 2. There's either the identity or it's sigma, the one which sends 1 to 2 and 2 to 1. These are the only one-to-one maps you would get, right? The sign of identity is 1. The sign of this map is minus 1. So let's apply this. Identity would give us F1, V1, F2, V2. The other permutation would give us F1, V2, F2, V1. And because the sign of identity is 1, we have positive sign behind F1, V1, F2, V2. And because sign of this other permutation is minus 1, because we have one intersection, we get a minus sign behind F1, V2, F2, V1. And note that this is determinant of a matrix where you have Fivj in its components. So that is true in general. F1 wedge up to Fk acting on V1 up to Vk is determinant of Fivj. So this is a good exercise to do to see you form this matrix. It's a square matrix. You take the determinant. This is your K. This is how this K form is defined on V1 to Vk. So as mentioned earlier, the space of alternating K forms is a vector space. Lambda KV star is a vector space. So again, we would ask, what is the dimension of this space, right? And as mentioned earlier, a good way to understand what is the dimension is try to come up with a basis for that space. So let's say V star as a finite dimensional vector space has the following basis, F1 up to Fn. Let's say they form a basis for V star. So if I pick k element out of these n elements, and if I look at their wedge product, this would be a k form. So it would be inside lambda k v star. The claim is that if I pick k elements out of these n elements, all of these kind of different choices would give me a basis. There are two things to note. First, the order does not matter. If you write fi wedge fj or fj wedge fi, if you change the order of these things which appear in the wedge, it doesn't matter because if you change the order of any two, you only get a minus one. And for the sake of constructing a basis, that amounts to nothing. The other thing to note that if two of these superscripts are equal, the wedge product would be zero. So I1, I2 up to ik, they must be k distinct numbers from 1 to k. Note that if I have fi1 wedge fi1 in this list, I can bring them together. If I change their order, I should get a minus sign. So fi1 wedge fi1 is minus the order change, but it's the same as the fi1 wedge fi1. So 2 times fi1 wedge fi1 is 0, which means fi1 wedge fi1 is 0. 0 tensor other things is 0. So the only way to construct a basis is to pick k elements, distinct elements out of n linear maps f1 up to fn. So that's the dimension. That defines the dimension. Also note that if k is larger than n, dimension of this space is 0. This can be seen from the property we mentioned above. Okay, so we have this notion of alternating k-forms. We know the dimension. They're essential in our multi-linear algebra, and they're essential in studying of manifolds. There are two more things we want to know about these maps, multilinear maps, alternating multilinear maps. One is interior product. For any vector you pick, any fixed vector defines a map from k forms to k minus 1 forms for any k. How is it defined? So let's say we denote this map with iota v. For any k form f, iota v of f would be a k minus 1 form. How is it defined? So if it's a k minus 1 form, I should, in order to characterize it, I should give k minus 1 vector to it as input, and I should say what would be the value of this. This should be a real number. I define this to be f of v, and then v1 up to vk minus 1. v1, v2 up to vk minus 1 form k, there are k vectors. F is a k form. F acting on k vectors is a real number. So you see iota v of f takes k minus 1 vectors and spits out another real number. So it's a k minus 1 form if it's alternating, and you can check that to see it is indeed the case. Okay, the second notion to define is pullback. Pullback of forms, which later will become pullback of differential forms. This is quite essential. Suppose we have two finite dimensional vector spaces, V and W. Suppose we have a linear map from one vector space to the other. Let's say T is a linear map from V to W. This would define a new map denoted by T star from K forms on W to K forms on V for any K. Okay, this is called the pullback map or the induced pullback map. Pick an element K form on W. I should define T star of F. It would be a K form on V. So in order to tell you what is T star of F, I should define its value on any set of ordered set of k vectors v1 up to vk, where each vi is a vector in v. I define this to be the following. So t of v1 is a vector in w, t of v2 is a vector in w, etc. up to t of vk. Now here we have k vectors in w. F is a k form on w. So F can act on any set of k vectors on W. So f of t of v1 up to t of vk makes sense. This is a real number. I define that to be the value of t star of f acting on v1 to vk. So you see T star of F takes K vectors in V and gives you a real number. So it makes sense for it to be a K form on V. You can check that to see indeed it is alternating. That's the way to define this. Okay, it's a good place to stop. See you.